basically, this lecture starts to put everything together, okay? So essentially what we're going to do is do some different 2D equilibrium problems. This brings it all together in the 2-dimension, and then next week we'll also look at the 3D equilibrium problems. Right now we're focused on just 2D, and your homework that you're going to have due next week is all going to be 2D equilibrium problems, okay? Because this is really kind of crucial, critical, the heart of statics, putting it all together, okay? Last time we did some work on doing free-body diagrams. Now we're going to use free-body diagrams. We're going to still do free-body diagrams, but also solve the problem, okay? And so I've got the first problem here, and recognize again, of course, we've got 3 equations. Some forces x, some forces y, some moments equal to 0, okay? So I got the first problem here, and it's a ramp, okay? And it says determine the force necessary to lift this ramp, okay? Determine the force necessary to lift the ramp, all right? And this happens to be a 200-pound ramp, all right? And so we always start off with the free-body diagram, okay? And so in this case, it says, okay, determine the force to lift the 200-pound ramp. So I'm thinking I probably need to draw a free-body diagram of the ramp. Now, there's really no need to draw the handrail and the connection between the handrail and the ramp. I think this is a sufficient drawing, something like that, okay, where this end point is point B and the other point is point A, like that. You don't need to draw a thickness to that or anything else like that. If there happen to be forces, notice the line between B to A. All the forces are pretty much on a line between B to A. There's nothing really relevant about the handrail or anything like that. If it happened to be relevant, for instance, let's say this rope, instead of being tied at C, shape as possible. You don't want to have to overcomplicate things, okay? So we got this, and now here's what I'm going to do. I'm going to draw a free-body diagram. So I'm looking at this thing, and I always ask myself 2 things. Look for the weight force, and look to draw all the points where this ramp is connected to other bodies' ground, okay, or whatever. And so you'll see it's pinned at A. That's probably where I start. And this here. It's pinned at A, and so I'm going to draw AX, AY right there for point A, okay? Because it's pinned, and I remember last time, you'll get used to pins because we do them all the time. Pins are very common, that we always just say AX, AY every time I'm a pin. Okay, that's easy. And then we've got this point G, probably somewhere like right here, and that's where the weight force is. Now you might say, how do you know the weight force is at G? Well, pretty much that's common. What we're going to do in this class is that we're going to put the weight force at point G. Point G meaning the center of gravity. You might be doing that in physics. So we always put the weight force at G, okay? And in fact, G will be used to indicate where the weight force should be placed. And weight is always down. So we say, okay, well that's easy. It's a 200-pound ramp. So we'll put that right there. Okay. Now, connected on this ramp at C, let me put C in there. Point C is a force. Remember, ropes always pull. We know that about ropes. So it has to look something like this. Okay. And I'm going to call it tension T in the rope. Okay. And it just so happens that up at the top by that pulley, it tells us that this angle here is 30 degrees. Oops, let's make that better. Okay, 30-degree angle there. And lastly, you look at point B. Question? No? Good? Okay. Lastly, look at point B, and you say, okay, it's parked there on the ground. Okay, it's connected. So we want to know, okay, what forces are on this ramp? So, well, it's touching ground there. And so I'm going to put a force from ground here, call FB maybe, onto the ramp. Because it's touching the ground there. Clearly in the picture it's touching the ground. So I'm thinking that there's going to be a ground force on the ramp. Because you always want to look where your ramp is touching. Okay? It's touching at A and it's touching ground at B, right? It's touching ground both at A and B, plus it has a rope. So those are 3 points you got to put forces on. Okay. So you get this Freebody diagram, but we got a problem here. There's a problem. And some of you may say, okay, maybe I don't see the problem. But the problem is, remember what I was telling you last time? I was saying that, remember, we have 3 equations. Some forces x, some forces y, some moments. And with 3 equations, I can only solve for 3 unknowns. And if you ever draw a free body diagram that has more than 3 unknowns, you're kind of stuck. In this case, my free body diagram has 4 unknowns. AX, AY, T, FB. My free body diagram has 4 unknowns. I'm stuck. I can't solve this problem. Now, some of you might claim that you can. Some of you might say, oh, I can solve this problem. No problem. I can do this. Somebody might say, well, let's sum moments about A, and then we'll also sum moments about B, and maybe we'll sum moments about C, and we'll sum forces X, Y. You can't do it. You can never solve a 2D equilibrium problem with 4 unknowns. You can't do it. Okay? So there's something wrong here. There's something wrong that I've done. And anybody identify what I've done wrong? Is FB equal to 200? How would I think FB is equal to 200? Remember, there's AY there as well. Because you could say, well, isn't this ground force holding it up? Yeah, but so is AY. Both sides are holding it up. So you can't really say that FB is equal to 200 because really the equation, if you were to write this equation out, and you can, you'd be saying this. Sum of forces in the y direction, up being positive. Really the equation is this. According to my free body diagram, it's FB plus AY minus 200 equals 0. According to my free body diagram, that is the correct equation. Yeah, that's what my free body is saying. Right? Because FB and AY are up, 200's down. So that's what my free body diagram is saying. So what's wrong? This can't work, because if I write out all my equations, I can't solve 4 unknowns.
Did you say that AY and FB are the same?
Oh, just to say they're equal to each other? The problem with that is, actually, I'm sorry. Hold on, I don't know what I'm doing here. Oh, hold on, sorry. Let me step back here. I goofed. This is not over. There's also a T. Sorry. T, it's probably you guys are like, what in the world is he doing? T cosine 30 is also there, equals 0. Sorry about that. So you can't, FB and AY are not necessarily the same because also that rope is pulling up too. I forgot, I'm just goofing here. The rope is also pulling up, right? T cosine 30. So that's also there. So they're all, Yeah, you can't really assume. It's got to be really dangerous to just say, oh, I don't know, let's just assume they're equal to each other or something like that. There's no real basis for that. It's still it's a normal force, right? Isn't that what we learn in physics? You probably learn in normal forces. But we don't necessarily know what it is. Yeah, but it is a normal force. Yeah, what you learn in physics.
So if the question is potential and cable.
Yes. Yes, exactly. Yes, there you go. So the point of this problem is to say just because you draw free body diagrams doesn't mean you automatically have to just blindly draw forces. Sometimes you have to think a little bit about this. And what it's saying, if you read the problem, is determine the tension T, the force in the cable, in order to lift the 200-pound ramp. The thing is, once you lift this, if you have enough force here to lift this ramp, that goes away because there is no longer contact at point B. Okay, that's the point I'm making by going through this exercise, is that sometimes you can just blindly throw forces on there, and that's okay, we're learning, but sometimes you have to think about this and go, well, yeah, that's true, but I have too many, what's going on here? Well, what happens is, if you have enough force for this cable to lift this ramp, then there's no more contact here. As soon as you lift this up like 1 millimeter off the ground, there's we ignore it. We just take it out of the equations. We just take it out. Oops, too many things out. Let me put this back in. We take it out, okay? Because it's not really there, okay? It's not really there. It's gone. Because once you have enough tension in that rope to pull up the ramp, you got all you need. And then this removes contact from the ground, and then there's no normal force there. There's no force from the ground onto the ramp. Okay, good. All right. So now, we have a little bit simpler case here. And I will tell you, and this happens in a lot of problems. This doesn't always happen, but it does happen in a lot of problems. And this is a problem that's one of them. You can go ahead and use this equation. And oh, by the way, you can also write out the x equation. The x equation looks like this. Sum of forces in the x direction equals 0, right being positive. And let me write it out for you, just so that you have it. It would be ax plus t sine 30 degrees equals 0. Right? Those are the only two forces in the x direction. Ax plus t sine 30 equals 0. You can certainly write these two equations out and use them, but I will tell you that a lot of times, a lot of cases, is if you can write a good moment equation, you won't even need to write the force equations, okay? And in this case is a good one. If you choose the right point to sum moments about, you don't even have to write anything else out. Because if you sum moments, you always want to try to sum moments about a point that has a lot of unknowns at it, okay? And in this case, point A is a great example. If you sum moments about A, AX and AY go through A, right? So AX and AY do not have moment about A. That's good, because it greatly simplifies the equation. A is where you want to choose here. In fact, there's only one unknown force that has moment about A, and that's the tension T. Tension T does have moment about A. What that means is that if I write some of the moments about A, I can do a direct solve and solve for tension T. I'm done. I don't even have to mess with those equations. Some force is X, some force is Y. I can do it much easier. And that happens a lot. A lot of times, if you can choose a good point for moments, it just breaks down and makes it real simple. Okay. So for instance here, let's go ahead and do that. Let's say some of the moments about A is equal to 0. Counterclockwise positive. Okay. Now what I'm going to do before I do that is I'm going to help you visualize this. The tension T, of course, creates moment about A. But the hard part for some of you this is not a big deal right now, but some of you are still having some trouble with moments. And so I'm going to try to simplify this, is that the hard part for students with this problem when it comes to moments of T about A is that you have to break up T into two components, and each one of those components has its own perpendicular distance to A that is because of the line from C to A. If you look in your picture from C to A, it's 9 feet. Okay? It's 9 feet from C to A. Right? But let's break up force T into two components. We have a horizontal component, which of course is T sine 30, and you have a vertical component, which of course is T cosine 30. Okay? So what's the perpendicular distance for the horizontal T sine 30? The perpendicular distance would be given by this blue line here. Let me just extend the green line here so you can see what I'm talking about. Okay? That perpendicular distance of this blue line is not 9 feet. It is 9 feet times the sine of 20 degrees, because this ramp is at an angle of 20 degrees here. You can see that in your picture. So that blue line there is 9 sine 20. Okay? So this is what makes it a little more confusing, is that because t has components x, y, and the distance from C to A has components x, y, you have to carefully put them all together or you'll screw it up. Okay? So let's do it. Sum of the moments about A equals 0. What do we got here? Well, let's take that t force. The t sine 30, that's the horizontal force. T, let's write it, t sine 30, okay? What's its perpendicular distance to A? Well, I already gave it to you. It's 9 sine 20, okay, that blue line, okay? So you say t sine 30 times 9 sine 20 degrees. And then you say, okay, well, is that clockwise or counterclockwise around A? This line here, the t sine 30, looks to me like it's going counterclockwise around A. So that's positive. Okay? How about the t cosine 30? That's the vertical force of t. Okay, well, that's t cosine 30, so I'm going to write that out. T cosine 30. Its perpendicular distance to A is not 9 feet, but instead 9 cosine 20 degrees. Okay? And it looks to me, if you take a look at that vertical force, it looks to me like it's going clockwise around A. So that's a negative. That's a negative. Okay? So that gets a little confusing because you have not only the force at an angle, but the distance between C and A is at an angle. So both those have to be broken up into their own components. Okay? That's the way I would do it. Now some of you might say, why don't I just do R cross F? Sure, but to do R cross F, you're going to have to break up into components. Okay? And then lastly, we're not done. That's not the only moment about A. There's one more, and that is the 200-pound force there at G. The 200-pound force also has moment about A. It's going to be 200 pounds times its perpendicular distance to A. If you go from G to A in your picture, it's 6 feet. But the perpendicular distance is not 6 feet, okay? It's not this line, right? It's instead this line, the green line, right? And so the green line there is not 6 feet, but instead 6 cosine 20 degrees. That's the perpendicular distance between the 200-pound force and A. And that 200-pound force, to me, it sure looks like it's a positive moment about A. Okay? So there you go. That's the whole equation. You set that equal to 0. And then the only unknown you have is t. So now it's just a matter of plugging it into your calculator and solving directly for t. And it turns out if you do that, you should get t equal to 195 pounds. Now, you didn't have to choose A. You could have done the moment about C. You could have done the moment about G. You could have done a moment about point D up at the top. You could have done a moment about D. There's some advantages about choosing a point that's straight above A at D. You know, if you could have worked it all out, yeah, you could choose that point. Might have been helpful too. I don't know. So there's different ways of doing it. And, you know, but I think A is the easiest, doing some of the moments about A. Again, here's the equation. It's always easier if you can write one equation, one unknown. If you have to have two unknowns in one equation, that means that you have to solve them simultaneously or use a matrix method or whatever. That gets messier. Which we'll do quite a bit.
I just want to make sure, you said the 200 pounds positive because it's pulling down, so it's going.
Yeah, look at, let me write it right here. How is that turning about A? Doesn't it look like it's turning that way around A? Yeah. That's a good question. Just make sure you see it. If you can see it, it's turning A that way, and my arrow that I've drawn there in red is counterclockwise, so that's positive. Okay. Let's do another one here. Take a look at this guy. Okay, it says here, determine the necessary counterweight at B in order to keep the 200-pound man with center of gravity G2 from tipping. Okay? The structure weighs 120 pounds and has center of gravity at G1. Okay? Notice here, the center of gravity G1 is not actually on the body. Okay? Sometimes students get confused by that. But the center of gravity doesn't actually have to be on force. Okay? So let's go ahead and draw a Freebody diagram here. Draw it as simple as you can. I would draw it like this. Here's my base here from C to D. Okay? Then I'm going to draw here. I guess I can draw something like this. I'll draw a little bucket, I guess. I don't know. If you want to. You don't really have to. You don't even have to draw that piece if you don't want to. Doesn't really matter. And then what you've got here is G2. I guess we're going to say this guy is about 200 pounds. And he's kind of leaning over, which is a worst case scenario here. So this is G2. So I'm going to say his weight force here is 200 pounds. Okay? And we're making it a worst case scenario because he's kind of leaning on the side of the bucket there, it looks like. Okay? Clearly this thing, if it were to fall over, he would fall to the right. There's not really a way for him to fall to the left, unless it's some crazy wind force or something like that. Right? He's got to clearly fall to the right. Okay? And so if he's leaning over to the right, that's going to make it easier for him to tip this thing. And it looks kind of like that's what he's doing. It's the 200-pound force there. It's 2 feet from the tire at D, if you look down there. Okay? And then you got a weight force of the structure, I guess, which is putting it right here. And that is 120 pounds. Okay? At that point, G1. Right? And then we got to figure out what counterweight we need. We don't want this guy to tip over, okay? This thing must be some kind of like cherry picking type vehicle, or it could be like a lineman or something like that, or maybe a painter or telephone repair or something like that. We've seen vehicles like this. It probably goes up and down in the bucket. And the one thing we don't want to have happen is have somebody tip over, okay? Because that would be a horrible thing. There incidents like this have happened where people have fallen over and stuff like that and died. So we don't want that to happen. So we prevent that from tipping by putting counterweight at B. Okay? So we want to figure out, well, what's basically the minimum amount of counterweight we're going to need here. So I'm going to put WB. It's basically a counterweight at B there. Okay? Now lastly, the tires are touching ground, and ground provides a normal force. Something's got to hold this up. One thing you got to remember with Freebody diagrams, there's kind of like a balance to things, right? Life has balance. Everything in life has a balance. In engineering and in statics, there's a balance. For every downs, you have to have ups, and for every lefts, you have to have rights. Okay? And so we have a balance. If you have three forces down, you got to have at least something coming up, at least one. Okay, in this case, holding it up, got some kind of weight force on the tire here, or some normal force on the tire, FC, and some kind of normal force on the tire, FD. Basically the ground holding up the structure at the tires. Okay? Now, those of you who have been trained to look for this will say, hold on, okay, this is good. This is good. We only have three unknowns. I don't know WB, I don't know FC, and I don't know FD. And so you're feeling good about this Freebody diagram because you're looking at this and you're going, you know what, there's only three unknowns. Dr. Reynolds has told me with a 2D equilibrium problem, I can solve for three unknowns. And that's correct, okay? But in this case, there's a problem. It's always got to be a problem. This is another one that has a problem, okay? Remember, well, I have three equations, right? Remember, I have three equations. I have some forces in the x equals 0, some forces in the y equals 0, and some moments about some point, I just say A in general, equals 0, right? I have three equations, therefore I have three unknowns. I can solve for three unknowns. In this particular case, one of those equations really is totally irrelevant. Yeah, you see that? Some forces in the x is pretty much an irrelevant equation here. You see that? Because there's no forces in the x. None of those forces have any component in the x direction. You see that? All of these forces are either up or down. There are no forces in the x direction. Therefore, that equation really is irrelevant. If you were to write that equation out, it would basically say 0 equals 0. Because there's no forces in the x, right? So in this case, you really only have two equations. Some forces in the y equals 0, and some moments about a pointer equals 0. That's all you got. So unfortunately, now that you've lost an equation, you've lost the ability to solve an unknown. You can only solve for two unknowns, and I have three. So what are we going to do here? Apply what we learned on the last problem to this problem. Yeah, they're not necessarily equal. You can't say that they're equal again. Try to avoid saying that because you really don't know. Yeah.
Aren't you trying to make it equal?
No. Oh, to balance it? We're not trying to balance it. We're trying to prevent it from tipping. Yeah. Those are two different things. Yeah. Yeah, and that's another thing people will, and I want you to prove it to yourself. Try this. Because I know a lot of people think, oh, why don't I just do two moment equations? Wouldn't that give me another equation? I know it looks like you think you will get another equation. You won't. It doesn't help you solve anything to write two moment equations. You can only use one. You can say, yes, a moment equation about C and a moment equation about D would look different. They would look different, but they really wouldn't be any different. Okay? They would be the same equation. Okay? What we do, and I heard somebody mention this, is because we're talking about keeping it from tipping. It says determine the necessary counterweight at B in order to keep him from tipping. We have got to look at what we call impending motion. Okay? And the analogy, a good one is if you get on a chair, and these chairs aren't a good example. The one over there by the board, and you tip back, there's a point where you tip back and you kind of go, whoa, you don't want to tip back anymore, right? Because you're impending to fall over, right? Somebody go try it. So, yeah, it's called impending motion. You're about to tip over, and most people, their heads can sense that. They kind of go, this ain't safe anymore. I better get down because I'm about to fall over, right? That's what we want to look at in this case. We want to look at the impending motion. We want to look at that point where this thing is just about to tip. And I bet you if you're in that thing and it's just about to tip, you'll know it. You'll be like, whoa. fast. Okay, what that's saying, and I heard somebody mention, is that basically, look at point C there. We know this thing has to fall to the right, and since it has to fall to the right, this point C is basically going to leave the ground. Okay? So this force at C is going to be okay? So what we do is we solve this by eliminating FC. And we say, okay, if it's just about to tip, then that's what's going to happen. It's going to be just like this. Because it's just about to tip, that tire at C is going to basically pull off the ground. Just a little bit. Just a little bit. And that's the point where we're going to look at the equilibrium. This is going to be our worst case scenario. Okay, now, what do you want to sum moments about then to solve this easily? D. Reason, again, you generally want to solve moments about places where you have an unknown force that you don't care about. I don't care about FD. I don't care about the force of the ground up on this thing. I care about what counterweight I need. So I choose D because it eliminates that unknown force. In fact, mathematically, this is going to be a fairly easy one. Sum of the moments about D equal to 0 gives me the following equation. Okay? The first one is going to be the weight force at B, the unknown counterweight. We'll call it WB. Right? Its perpendicular distance between B and D, if you look in your diagram, the perpendicular distance between B and D, 7 feet, right? 7 feet. Okay? And if you look at your diagram, your Freebody diagram, you'll notice WB is a counterclockwise, right? It's counterclockwise around D, so that's a positive moment. Okay? And what else we got? Well, we got the 120-pound force at G1, right? So we got 120 pounds. And the perpendicular distance between G1 and D is just 1 foot, right? Just 1 foot. And that is also a positive moment. If you look at it, that also is a positive moment about D. It's counterclockwise around D. So we'll call that a plus. And then finally, you've got the 200-pound force of the guy. The perpendicular distance between that and D is 2 feet. Clearly in the picture is 2 feet. And the guy has a negative moment about D, right? That's going to be a negative because it's going clockwise around D. His weight force of 200 pounds. That equals 0. Now the math here is a lot easier to solve for the counterweight. The counterweight's a lot easier because you've got, it's basically 120 minus 400, and then you bring it to the other side. So it's 280 divided by 7. It turns out to be easy. It's 40 pounds. So, 40 pounds. That's your answer. That's the counterweight necessary to keep the guy from tipping. Now, let's say you weigh 200 pounds and your friend the engineer has correctly done the calculations and said, oh, let's put 40 pounds of counterweight on there. You feel pretty good about going up in that cherry picker? No. I think, yeah, he did the correct calculations or she did the correct calculations. There's nothing wrong with it, right? But usually what we like to do is put a safety factor in things. Yeah, I'm thinking to myself, okay, it takes 40 pounds. I'm going to throw a safety factor of 3 maybe and put 120 pounds at B, okay? Therefore, if we're a little off, the guy ate too much this morning, had too many pancakes, and he's 210 pounds, or something crazy, if we're a little off here, then the thing doesn't just tip over too easily, right? We put a safety factor in things, okay? It's important that we learn exactly what we need, right? It's good to do the analysis, but then it's good to put a safety factor, okay? Elevators, the cabling that holds the elevator up has a safety factor of about 20 typically, meaning that it can hold up about 20 times more than what that weight is on the elevator door, okay? So that, it's not going to break the cable, at least, okay? Now, your motor may not be able to lift 20. The motor for the elevator may not be able to lift 20 times more, but at least the cable won't break, Okay, so because they got to factor in a pretty good safety factor to make sure the cabling doesn't break and stuff doesn't break in an elevator. Anything that involves humans doing things like this, you don't want to have a safety factor of 1. Okay, you want to have a safety factor of 2 or 3 or 4 or whatever. Okay, if you can. Okay, if you can. All right, if you can. Okay, but that's the minimum needed. That's Freebody diagram. Okay, and a moment. Now we could have wrote forces here, but we really didn't need to. A lot of times you do a good moment, you can do it. All right, let's go to the next one. Go to the next one. Okay, this problem, this is a problem where if you draw, you can draw a correct free body diagram. You can do everything. Okay, now before we get into the actual free body diagram itself, let's do a refresher or reminder here. We got another spring, okay? I don't want you to forget about springs because they come up from time to time. Okay, so it's a device used to hold an elevator door open. It has a spring with a K of 40 newtons per meter. The spring, it's compressed a distance of 0.2 meters. So the spring is compressed 0.2 meters. Okay, determine the reaction at A and B. All right. So let's first think, okay, I see this bracket of some sort, this bracket that's connected between A and B, and we got a spring. That spring is somehow involved in that thing. Okay, so let me draw the bracket the best I can. I'm not a great drawer. Something like that. And then you've got A. It's pinned at A. So you say, okay, AX, AY, okay? And so before I look at B, let's talk a little bit about that spring, because people will have trouble with that spring. Okay? Remember that springs can either be in compression or they could be in tension. Okay? Springs in compression, they always push. Okay? Springs in tension, they always pull. Okay? So it says the spring is compressed. Okay? The spring is compressed. That means it's being pushed in on both sides. If it's being pushed in on both sides, it also pushes out. Okay? So the force on that bracket will be down. It will be down. That force will be down like that. And how much is that force? Well, remember a spring force. The force of a spring is simply equal to kx. Okay? Where k is the spring constant, which in this case is 40 newtons per meter, and x is how much it's either compressed or stretched. In this case, it's compressed a distance, it just tells me, of 0.2 meters. Okay? So this is pretty easy. 40 times 0.2 meters is equal to 8 newtons. Okay? So this spring is compressed 8 newtons. That means that it's pushing down, it's pushing basically on that bracket 8 newtons. Okay. By the way, to remind you, sometimes we express that x, we won't say x, we'll say x minus x naught, remember? Where x naught is equal to the free length position. The free length of the spring. Remember that? Sometimes we call it free length of the spring. In this case, you don't need to know that. It just says it's compressed a distance of 0.2 meters, 20 centimeters. That just means that it's, that is x minus x naught, basically. Okay. So anyway, that's a whole long thing, but basically remind yourself, give you more practice. I want to try to find a spring problem for your next homework so you can get some more practice with springs. And how about B? Well, look at this. It's pinned at B. So if it's pinned at B here, this bracket piece, you're going to have a BX By. And that's it, right? I mean, there's no weight force in this bracket. It doesn't tell me the bracket weighs a certain amount. So there's no weight force in the bracket. That is a free body diagram, and that is a correct free body diagram for what I have drawn. There's nothing wrong with that free body diagram. I promise you. Not trying to trick you. There's nothing wrong with that free body diagram. Okay? But you can't solve it because you have 4 unknowns. You can't solve it. So there's nothing wrong with the free body diagram. I don't want to give you the idea that there's anything wrong with that free body diagram. The problem is I've drawn the wrong free body diagram. Okay? There's nothing wrong with that free body diagram. I've just drawn the wrong free body diagram. And this gets where it gets a little tricky. Because sometimes you could just, okay, if you tell me to get the reaction forces at A and B, I'm going to draw this bracket that has A and B. And I got it. There you go. I'm going to draw. You don't have to draw the free body diagram like this. Okay? Here, I'm going to show you another way to draw it. This way is going to be a little different. Okay? Here's what I'm going to draw this time. Like that. Where this is B, here, this is A, like that. Kind of running out of space here. I should have moved it up a little bit, but I think you get the idea. Okay? Now, why is this one a better free body diagram? Now, let me draw the forces still. Oops. Sorry. This is AX. This is AY. Got to move this A here. This is A. Hopefully you have more space. Make a little more space than I did. I drew it a little too big. Okay? Here's why this is better. Oh, don't forget the 8 Newton force still here. Okay? Here's why this is a better free body diagram. Point B, and this is a concept that's very important, that it's hard to see. Some of you will see it right away, and some of you won't. That's okay if you don't. Okay? But hopefully eventually you will. Point B is now internal. It's internal, inside. I do not draw any forces at B because B is but I have included the rolling thing into it. So this is where it's going to get a little messy. But I'm going to have to draw a line here for that. And this line, of course, is at 30 degrees. So hopefully you have a little more space than I do. But, okay. Now, that roller is in contact with the surface below it. And because it's in contact, that's a rolling contact. And if you go back to your notes from the past lecture, you'll realize that means there's a force perpendicular like this. Call it force F. It has to be perpendicular to the contact surface. Sorry it went down in there, but I think you get the idea. Okay? Now, here's the beautiful thing. The way I've drawn this now, I only have 3 unknowns. I eliminated an unknown by drawing my free body diagram a different way. This way, point B became internal, and now I only have 1 unknown force there at the end. Because it's just a rolling contact. It's a roller, and if you look at a roller, previous lecture, roller means force that's perpendicular to the surface, like that. Okay? That's great, because now I can solve it. So how do I solve it? Okay, well, what you want to do is write a moment equation again. Those are always nice. Okay? Write a moment equation. Okay? it turns out that I would suggest that you write a moment equation about point B. You may not agree with me on this one, but that force F, its line of action goes through B. It will have to go through B, okay? Because point B is basically in the center of that circle. I may not have drawn it very pretty on my picture, but if you look at that diagram, point B is the center of that circle. So that force F has to go through the center. That force F has to go through the center. So what that's saying is if I do the sum of the moments about B equal to 0, okay, here's what I got. I only have 3 forces then that create moment about B. And I apologize, I'm running out of space. I should have put this other one on the other page. I may have to work a little bit down below too, just to get our space here. But if I sum moments about B here, counterclockwise positive, what I've got is just 3 things that create moment about B. Okay, I've got the 8 kilonewton, sorry, the 8 Newton force. The 8 Newton force has a perpendicular distance to B, if you look at the diagram, of 125 millimeters between the 8 Newton force and B. That's, I'm talking about right here. 125 millimeters. That's what your diagram says. Okay? So I'm going to put this in meters, right? And it's going to be 0.125 meters, because I don't want to do millimeters. I like meters. So we're going to say 8 newtons times 0.125 meters, and if you look at it, that's a positive moment about B, because it's counterclockwise about B, the 8 Newton force. Okay? You see that? Now how about the AY? How about that vertical force at A? Okay, well that's going to be AY times its perpendicular distance to B. Well, that's all the way across, and if you look at this other part here is 150 millimeters, right? So if you go all the way across, that's going to be AY times 275 millimeters, which is 0.275 meters. So it's going to be AY times 0.275. Okay, and that's going to be a negative moment, so that's minus. Okay, and then there's one more, and that's AX. AX, if you do its perpendicular distance to B, it's clearly 100 millimeters if you look at the picture. And so it's going to be AX times 0.1 meters. And that's also going to be negative. It's also clockwise about B if you look at it. And that equals 0. Okay? I'm going to redraw that equation. I'm going to rewrite that equation down here just so you can see it. Sum of the moments about B equals 0. You've got 8. You got 8 newtons times 0.125 minus AY times 0.275 minus AX times 0.1 equals 0. Okay. Now you can't solve that one just on its own. Okay, you can't solve that one on its own. You're going to need, this case, you're going to need to write the other 2 equations. Okay, you're going to have to write sum of forces in the x direction equals 0, right, being positive. Okay, and what forces are in the x direction? Well, only 2. AX, this is going to be AX, and a component of F is going to be in the x direction. Now, some of you may have trouble visualizing this, but if you look at this picture here with F, if you look at this F, okay, if it has a 30-degree angle, you can draw a triangle like this. If this is 30 degrees here, this must be 60 degrees there. And if you see it that way, then you realize that the component of F in the x direction is going to be equal to minus F cosine 60. Cosine, and it's left, so it's negative. All right, those are the only 2 forces on that bracket plus roller that are in the x direction, is the AX and the minus F cosine 60. And then finally, there's one more, and that is sum of the forces in the y direction equal to 0, up being positive, and you've got AY. You've got minus 8, because that's the spring force down. And then you've got plus F sine 60, because that's the F force up, F sine 60. You got 3 equations, 3 unknown. So your best method of solving 3 equations, 3 unknown is a matrix. Okay? 3 equations, 3 unknown. Your best way of doing it is a matrix. Yes. Matrix. Because really, I mean, substitution is going to be kind of messy in this one. So let me do this just for your own benefit. Let me put this in matrix form for you and make sure you know how to do this again. Yeah, why? It just, yeah, you could. You could. I mean, there's nothing against that. I'm not, it's fine. Nothing wrong with it. It just, I wouldn't recommend it. I mean, if you know how to do the matrix method, it's going to go faster. Set it up, AX, AY, F, some order like that. If you take a look at that top equation, or actually, let me see. I kind of, okay, I mean, you could redo the order if you want to. It doesn't matter. If you look at the second equation, it's AX minus F cosine 60, so I did it like this. If you look at the second equation, it's AY plus F sine 60, so I did it like this. And don't forget the other side. The other side, this has to be a 0, but this has to be 8. And then the bottom one is basically the moment equation. So this is going to be 0.1 AX minus 0.275 AY, 0F, and that's going to equal, if you work this out on the other side, minus 1. Because 8 times 0.125 is 1, but you bring it over to the other side. So let me remind you of that. This is 8 times 0.125 minus that there. So that's in matrix form. Then you can go ahead and solve it. If you solve it, you get the following. AX happens to be equal to 3.19 newtons. AY is equal to 2.48 newtons. And F is equal to 6.38 newtons. Okay. So it's basically asking you for AX and AY. Now, that's not really the whole picture there. That's not the total answer if you look at the original question. By the way, the original question didn't even ask for F. I got it anyways. If you look at the original question, it says, give me the reactions at A and B. Well, you gave me the reactions at A, but you didn't give me the reactions at B. Well, how do you get the reactions at B? Well, you probably, the easiest thing would be, is to go back to the first free body diagram I drew. Okay? So I'm making sure if everybody's written down the numbers, I don't know. I'll go back to it in a second. If you go back to the first free body diagram I drew, up here at the top, it's very easy to see that AX plus BX equals 0, right? Because there's no other, right? Since looking at this top one, AX plus BX equals 0, right? And since I already know AX is 3.19 newtons, therefore BX has to equal minus 3.19 newtons. Why is it minus? That just means it's I drew it in the wrong direction. So what? Okay? And since AY plus BY minus the 8 newtons from the spring equals 0, and I know that AY, look down here, is 2.48 newtons. 2.48 plus BY minus 8 equals 0. So 8 minus 2.48, like 8 minus 2.5 is going to be what? 5.5? So it's going to be like 5.52, I think, is BY. So that's how you get the full answer. Sometimes you have to draw two free-body diagrams and work from both of them. Okay? Now, that's a little more complicated than what we're getting into right now, but in a few weeks from now, we'll be there. We'll be taking multi-body systems and taking them apart and putting forces all over them and solving different ones. Yeah?
Can you go back over the matrix, like how,
Sure.
like...
Okay, now recognize this, and this is where I may have confused some people. Recognize that this top equation ended up down at the bottom row. And then the second equation is the top one, and the third equation is the middle one. Okay? And so if you take a look at the bottom one, okay, that bottom one, you can see it if you look at that top equation. It's, okay, it's, let's see here. Oh, hold on a second. I think I forgot to put a minus there. I'm sorry. I think I forgot to put, yeah, I forgot to put the minus. There's a minus here. Sorry about that. It's minus 0.1 AX, so minus 0.1 times AX, minus 0.275 times AY, and there's no F in the top equation, so it's 0. And then this minus 1 comes from the fact that on the top equation I have 8 times 0.125. Well, 8 times 0.125 is 1, but I bring it to the other side so it becomes minus 1. Okay? Now if you look at the top equation, that's the second equation here. It just says AX minus F cosine 60 equals 0. Well, 1 times AX plus 0 times AY plus minus F times minus cosine 60 equals 0. Okay? That's how you get it. And the same thing for the other one. It takes a little while. The only thing I can tell you is it's so much better if you do it on your own and play with it. How you said it. Okay. Well, we're out of time to do the last one because we're going to do a quiz. We'll get to the last one later.